So we're going to look a little more closely at error and how we might propagate it through calculations in lab. So say we have a box. It has a length and a width and a height that we can measure with a ruler. And each one of those rulers, we use different rulers, and so we have different amounts of uncertainty with each one of those things. If we look at these uncertainties, the uncertainty that we read off of our measurement device, off of our ruler or our calipers, this is called absolute uncertainty. Sometimes it's represented by a capital letter A, which is what I'm going to be using here. It has units of the measurement. So this is 6.7 centimeters plus or minus 0.3 centimeters. Okay, and I'm going to keep with my sig figs here, and you'll notice that the first uncertain digit here, right, is where your uncertainty lies here as well. We can also define the relative uncertainty, which is the absolute uncertainty over the measurement itself. Okay, so 0.3 is my absolute uncertainty over the height, the actual measurement, and that gives me a fraction, 0.045. If you were to multiply that by 100%, you get 4.5%. So this relative uncertainty tells you that I know that the length of this box or the height of this box is 6.7 centimeters plus or minus 4.5% of that measurement. So this can be helpful sometimes in other ways. This is representing a fraction, but you'll notice that because these two things, the absolute uncertainty has the same units as the units of measurement, those units cancel, and relative uncertainty has no units. Okay, so sometimes this is called fractional uncertainty. This is a percent uncertainty, but they all represent the same thing. Now, say I want to determine the perimeter of the top of this box. Okay, so I'm going to add the length plus the width plus the length plus the width together to get the perimeter of the top. And you can do that math. This is going to be a sum, and we have 16.4 centimeters. Again, following my sig fig rules where I'm keeping the least number of decimal places, which is just one decimal place. What is the absolute uncertainty in the perimeter of this top? Because if I have uncertainty in each of these measurements, I must have uncertainty in the answer. The way we calculate the absolute uncertainty in the answer in this case is to square and sum the absolute uncertainties of all the pieces of that calculation. So we do this anytime we have addition or subtraction. So if the mathematical function that we're using is addition or subtraction, we need to sum all the squares of the absolute uncertainties. So I can plug that into this equation. Again, 0.1 squared plus 0.2 squared plus 0.1 squared plus 0.2 squared, and then take the square root, and I get 0.316. So the answer to the question, what is the absolute uncertainty in the perimeter of the top, would be 16.4 is the actual perimeter, plus or minus 0.3 centimeters would be my absolute uncertainty. Okay, so this this process again is for when you're adding or subtracting values that have uncertainty associated with them. What I want you to notice is that these two uncertainties that were used, anytime you propagate those uncertainties, your final answer will have a larger uncertainty than what you started with. Okay, so anytime you manipulate measurements, you are introducing more uncertainty into your answer. So we've got this box, and maybe we want to find the volume of this box. If we want to find the volume of the box, we're going to multiply the length times the width times the height. So we can do that. 5.9 times 2.3 times 6.7 is going to give us an answer. And again, here I haven't stuck to my sig figs yet. I should only have 2 sig figs, so I'm keeping 1 extra digit just for rounding later. But in order to find the absolute uncertainty in the volume, what is the uncertainty in this calculation, we need to calculate this a little bit differently than we did for addition and subtraction. If you have multiplication and division, you need to use this equation instead. We can find the relative error in the answer by using the relative errors in each of the pieces squared. Right? So the same way that we used absolute errors in the last problem, we're using relative errors here. And that means we have to find the relative error of each of these measurements first. Okay, so here I've got the relative error in the height. Again, in order to calculate that, I've got the absolute error over the measurement itself. I've got the relative error in the width and the relative error in the length. Okay, I'm representing them here as a fraction and as a percent, so it might be a little more intuitive to think about. And then I can plug those relative errors back into this equation. So if I use the fractional forms, I'm going to get a relative error that's 0.99 or 9.9%. Okay, so the answer to the question, what is the absolute uncertainty in the volume, means we have to turn our relative error back into an absolute error. Now, in order to find the relative errors in the first place, we took the absolute error divided by the measurement, and we're doing the same thing here. We're trying to find the absolute error divided by our answer, okay, and we're going to set that equal to the relative error. It's the same equation, we just have a different unknown in this case. Solve for A, okay, cross multiply, so I get 9. Now my answer to this question, 91 plus or minus 9 centimeters cubed. Again, I want to point out very clearly that my relative error in my answer, or the error in my answer in general, is greater than the error in any individual measurement that goes into this calculation. So here, the error for the length was 1.7%. The error for the width was 8.7%. The error for the height was 4.5%. And when you get your answer, the error in the answer is 9.9%. So we're almost at 10% here. That is larger than any of the other error values. Okay, so this is a really important point to keep in mind. The error in your answer will always be larger than the largest error of any constituent points. So if you think about in lab when you're doing measurements and you have a mass measurement and you have a volume measurement, perhaps your mass measurement has less relative error, maybe 0.1%, and your volume measurement has a lot higher error. Your error in that calculation for density would be completely determined by the error in the volume. Okay, it's going to be larger than the largest uncertainty that you have.